Hello, this is Graham Boswell of Spectral Measurement. Today I'm going to show you how we set up the dScope system to measure a loudspeaker driver, and then how that test can easily be automated for a production QC test using our Autosequence automation tool. This can be done on the bench with the accompanying acoustic limitations, as indeed here, or in an anechoic chamber, or using one of our loudspeaker test chambers to obtain a calibrated equivalent free field response. For this example, I have a Bose S1 active public address speaker on my workbench. So let's get started. This is the dScope. It's described comprehensively in another video, so I'm going to dive straight in and open the LSS automation tool for electroacoustic measurements. The LSS tool is actually a scripted application, and that means it's free to use, and you get the source code and obviously could customize it to your own needs if you want to, but it's a pretty comprehensive tool as it stands. It also integrates with our Autosequence tool for the purpose of automating the electroacoustic tests that we set up with it. So let's have a look at the LSS tool. First of all, we need to check the microphone calibration. If we have a look in here, we can see that we can use a calibrator, or we can set a mic sensitivity and, if necessary, a preamp gain. We can also apply a microphone frequency response correction curve separately in the dScope FFT parameters. That would be over here in this pre-weighting selection, and that would be a user weighting. And we're using the built-in phantom power for the microphone at 48 volts. We don't have a current sense resistor connected in this setup, and that will have some implications as we'll come onto later. So we're just going to measure the frequency response and distortion. Okay, so we're done with our calibration. Let's have a look at some other setup parameters. Here we set up the sweep range. Now we're doing a Log Swept Sine sweep, so a continuous sweep over a range of frequencies, and the range of frequencies is set here from 10 to 20 kilohertz. We're driving 200 millivolts into our active speaker. We're using 32K FFT points, a good compromise setting in a way that is reasonably quick to execute and gives us a reasonably good frequency resolution. The frequency range of the measurement is 22 kilohertz, could be greater. The sensitivity range, now this is important. If we want to determine the sensitivity of the speaker, we usually want to specify a range over which that measurement is made, and that is made in this case between 100 Hz and 10 kilohertz, and we're using a non-inverting microphone. Down here we can choose some graphical results that we're going to display. We're going to, in this case, display individual distortion harmonics. We could display a composite THD as well. We could add a rub and buzz result. We could add an acoustic phase measurement and an impedance measurement. Well, we can't do the impedance without the current sense, so I'm not going to be choosing that. We can also apply smoothing with a range of ratios from 1/24 to none at all, being unity. So that is our setup. Before we finish there, we need to just set up some gain ranges and make sure that the instrument is acquiring a signal. So I'm just going to hit the apply button, but before I do that, I'm actually going to connect the speaker because it's not connected at the moment. So there we are, connected, and apply. So we've acquired an impulse, all seems to be set up correctly, and we can click OK, and we're ready to make our first test. And we do that simply by clicking Run Test. And there we've got a frequency response and the distortion harmonics, and you can see how quickly those results are obtained. At this point we could save our setup. We might want to save as, give it a different file name. We might want to open a different test. Here I've only got one set up at the moment, which is the one that's currently loaded. And obviously then we can save tests for different purposes or for different types of speakers and so on. Regarding the results, we're going to move on to talk about automation, but before we do that, I just want to draw your attention to some of the other results. We saw in the setup panel that we chose a range of graphical results, but in addition to those, we've also got the overall level, dBSPL, the polarity of the speaker, the distance from the acoustic source to the microphone, and if we had a current sense, we could have our sensitivity in dB at 1 watt per meter, as well as the resonant frequency and the DC impedance, the Z-min. Yeah, as we don't have a current sense, we won't get those results. So we've got several scalar results and we've got some graphical results. If we want to plot these graphs, we can select the graph in the legend that we want to plot, say for example the fundamental, and come to the plot control here, and I might want to change this and call it frequency response, for example, and export. Now let's just check our print preview settings. We're not going to go black and white. We're going to have a title, scales, we're going to have the legend. We're going to have a comment. This is a comment about my Bose S1 test, and then we'll run the print preview. It's actually showing up in black and white. That'll be because of the print driver that I've got selected. So we'll go to print setup. I'll choose something that will allow me to print in color, and then we will see if there's a color result. And you'll see on there the markers for the sensitivity range, scales, and so on, and the comment that we'd added at the bottom. So now we're going to just have a look at how this integrates with Autosequence. Just before we start, if we want to set up a series of plots, here we plotted just the fundamental. We could have added the second and third harmonic on the same graph, or we could have done a separate plot for the harmonics, like this. Of course, I'd want to change the harmonics response. So there's our harmonics response plot, for example. So we plotted a couple of different results there, but for the automation, we want to tell the Autosequence what plots we would like to include. And if we're going to write the results to Excel in our automation in a tabular format, we need to define which results we want to tabulate. So we have our graph selection for exporting various traces. We assign traces to graphs. So we could plot them all on the same graph, but what we're doing is we're specifying two graphs. One's called frequency response and the second one's called harmonics up there. The others are not currently used, nothing on the specifications for any of those. But the first two, we've got second and third harmonic on graph 2 called titled harmonics, and we've got fundamental on graph 1 titled frequency response. In the bottom box you'll see traces to Excel. We've just got the fundamental, and the graph selections don't affect the Excel box, so that's just a separate box for which traces we want to include in the Excel tabulation. There's about 400 points in this 24th octave curve, and that's 400 columns, so we perhaps want to be a little careful about how many curves we export to Excel. We just want to export the most important ones. We can have a large number of columns, but it just makes navigating the spreadsheet a bit easier if we don't have data we don't really need. So that's our setup for exporting graph information for the automation. So let's now load up the automation tool. I'm just going to pop that out of the way. We'll load up Autosequence, and we're going to select this particular speaker driver test. We're going to run it in the setup mode so we can actually see some of the setup and how the integration works with the LSS tool. So let's do that. So here's our spreadsheet. This has already been nicely configured, which is great. Having said that, the setup of the spreadsheet is in fact automatic. If we open the settings, we'll see here at the bottom we've got Excel report options, Excel reports and sweeps enabled. And if that's enabled, and if a spreadsheet doesn't already exist, and it would exist in the report folder, so I can open the folder. Now I've opened that on another window. Let's bring that over. So this is the report folder, various HTML reports printed, and there's our spreadsheet, the one we're looking at now. If it doesn't already exist, the first time you run Autosequence, it will create the spreadsheet and create all these headings and columns and so on, and format it so that it's ready to be filled in the next time. And you can save that as a template. If you want to create a succession of files, you can have over 1 million records per file. It depends on how fast your computer is and whether you feel that perhaps less than that number might be a suitable number, or you might do it monthly, or however you do it, you may end up with a succession of files. But if you have a very large number of records, it's quite easy to import them into a database like Access or SQL for more detailed analysis. We do incidentally have another automation tool that works directly with Microsoft SQL Server for high volume applications where we want to get everything into a database as quickly as possible. So that's an entirely separate tool that we'll cover in a different video. Just another quick note here. This checkbox under HTML options enables a separate HTML report file for each test. Otherwise it just creates one file and overwrites it each time. And the serial number prompt at the top is set. That means that when we start the test, we're going to get asked for a serial number. We can also, at that point, read it from a barcode reader with a little bit of extra script, which is something we usually help out with. We've got various examples for different readers. And we're going to show a pass-fail banner at the end. So there are various other options, but we won't dwell on them now. So we're ready to start. We're loaded. I think we'll just have a quick look at some of the test setup. This enables us to see which traces we're going to evaluate. The first two entries, LSS run and LSS success, are just there to tell Autosequence that it's doing a loudspeaker electroacoustic test. It's doing a test that's been set up by the LSS tool. And in those tests, we're looking at results of the fundamental. You'll see that in fact we could choose any of the three for any of these, so we can do them in any order. But these are the three traces that we've set up to export. You remember we set them in the graph exporting. And we're also picking up the acoustic level, which is the level indication up here, level in dBSPL, and we're applying a limit check to that. So it must fall in the range 85 to 90 dVSPL. Okay, so that's some detail about the test limits. You can actually see in my spreadsheet I've run a few rows without the serial number entry where we just get a date timestamp, and then I've started entering serial numbers about halfway down. One of the earlier ones I've got a fail, and in fact in the notes column, which you can fill in as you're going along, after the test, for example, I've made a note of various things I've done to modify the response, just so that we can see some variation in the data. And in this particular one, had my hand over the mic and the tone controls down, and we managed to fail on the dVSPL result being out of range. So we've got an indication there of the failure. Okay, so that's some data in the spreadsheet. What we're going to be doing is we're going to be seeing a new row being added each time we run the test. So let's now run the test, and we'll see what happens. First thing is I'm going to enter a serial number. Just to make it really obvious, I'm going to make it 999999, and we'll click OK, and Autosequence will then load the test and execute it. You can see it's now filled in that row, and it's indicated a pass. You'll notice there is a limit line on the result plot there, and that has been evaluated as part of the evaluation of the fundamental trace. Or it's not the limit line that's been evaluated, the fundamental trace has been evaluated with respect to the limit line, and the result is a pass because we're below the maximum limit. We're also in range for the dBSPL level, coming in at 87.91, that being pretty well in the middle of the 85 to 90 dB range that we set. So that all looks very healthy. One or two things to mention about this test setup. The frequency response can be displayed as a relative trace relative to a reference, and so in that way it would give a flat line. If we tested, say, a speaker, saved it as a reference and tested it again, the result would be more or less a flat line, and that makes setting limits much easier. But of course you still have a potential gain offset between the two, particularly if you're testing different speakers. And so you may also choose normalization, and you can do this at any frequency. So we can set, for example, normalization at 1K, so that in the resulting plot, the 1K point is always at 0 dB. And we're doing a relative plot, so all we're showing is the relative difference normalized at 1 kilohertz. So there's no need for shifting limit curves up and down or shifting traces up and down to see if they fit a limit profile. It's a very powerful technique. These limit lines can be created from a measurement. We can take a result and just shift the result up by a few dB and make that a limit line. We can create them from a script, perhaps calculating some limits or reading from a table. And one example might be to create a table in Excel where we use some statistical analysis to create an n times sigma limit curve. So if we go through the columns in our spreadsheet, for example here, if we look at a column, we can calculate for that column a standard deviation. We can multiply that by whatever number, 3, 4, 5, 6, and so on, and then we can set that as the magnitude of the upper and lower limit. And so in frequency ranges where you have more variance in the frequency response, you can have a little bit of a bulge in the limit curves, allowing you to achieve a sensible yield in your speaker production and not rejecting speakers because of an inappropriate choice of limits. So that's a pretty clever way of calculating limits, and in that way you'd be reading your statistically derived limit curve data from your spreadsheet, and you can read it in and set it as a limit curve in dScope. And alternatively, and most easily of all, in fact, you can do a piecewise linear approximation, which is what we have here, a very simple example. So if I select the trace, the fundamental, click on draw the limit line, then I can get hold of the limit and move it around like that. And when I'm done, press OK or cancel to leave it as it is. If I choose the limit curve itself and click on the list of values button, I can actually come along and change that limit. Let's say make that 98. And so I can edit the limits numerically as well. Let's come down a little bit. So I think that's all we'd like to cover today. We've seen how to test a loudspeaker with dScope and to automate that test and capture tabular results for QC purposes. My name was Graham Boswell. This is Spectral Measurement. Thanks for watching.